GM everyone! Today we're going to speak more about zkVerify architecture. For those who don't know me, my name is Milica. I'm a PhD candidate and DevRel engineer for zkVerify. So let me tell you more about zkVerify architecture. If there's a person who wants to use our product, we actually have a proof submission interface. Our users can do a bunch of things, including registering for a verification key, and the user has this methods available for each verifier, and there are a couple of those that you can find in our documentation. So underneath, we have several verifier palettes. You can think of palettes like a module and some sort of substrate lingo, and these palettes handle transactions or extensions that the user can invoke. So what happens next is that the user submits a proof, a verification key or VK. You can see that in our documentation as well, and public inputs. What they do is they pay for the proof submission. Alternatively, they can register a verification key once and avoid sending it every time, which actually saves costs. So instead of sending the full VK or verification key each time, the user sends only a hash of it. This reduces costs a lot because a VK can be large, typically around a couple of kilobytes in size, while the hash is only 32 bytes. We also perform VK checks only once during registration. So that saves some costs for the user. So costs in Substrate are determined based on the reference machine, a standardized hardware setup that validators use. Each extrinsic or transaction in Substrate is benchmarked against the machine to determine execution time. A benchmark runs on the worst case scenario, determining the maximum time required for execution. This time is actually measured in picoseconds and converted into wait. So what would the wait be actually? So the wait is determined both by the execution cost and how many transactions fit in one block. Validators can include extrinsics or transactions again in a block until they reach the 1.5 second limit. So the block finalization happens about 3 blocks after creation. The delay was increased to prevent stalls due to those validator processing constraints. So for consensus, zkVerify use BAPE for block authoring and Grandpa for finalization. So block authoring and block finalization, there are 2 algorithms, BAPE and Grandpa. These processes are separate and they allow for flexibility and upgrades. What that means is that updating either block authoring or finalization is theoretically possible, but it is complex due to deep integrations in both the runtime and node level logic. So let's talk more about fees. Fees in Substrate are derived from weight using a weight to fee function. Each extrinsic has associated weight, determining both its execution cost and block inclusion priority. So users cover the cost based on the worst case scenario time, but if the actual execution is faster, the excess fee is reimbursed. Just like you have refunds with Ethereum gas. You have gas refunds, right? And so what happens then is that the submitted proof is verified against the verification key and public input. If it's valid, an event is emitted, logging the verification status. Verified proofs are stored in the proof of existence palette, which maintains a list of verified proofs with a maximum size limit. Later on, we'll see kind of scheme of that. So I will create a schematic for you as well so that you can connect the dots. We will have also the storage size, which is capped to prevent unlimited growth and potential spam attacks that can actually clog the system. Once the storage limit is reached or a set time lapses, a Merkle tree is built from the verified proofs and a new attestation event is emitted. The attestation event is sent to an Ethereum smart contract via bridge, storing the latest attestation data on L1. Here, when I mention Ethereum, it can be any kind of L1, doesn't have to necessarily be Ethereum, but most of the people are familiar with Ethereum as a blockchain and its smart contract. So most of the time I will then mention Ethereum, of course. A bridge is required to transmit attestations to Ethereum, of course. While a testnet script can simulate this, a bridge is essential for full functionality. The zkVerify smart contract on Ethereum stores the last attestation and provides methods for publishing attestations and verifying proofs. Users can call a zkVerify API to obtain the Merkle path for their proof. Once the attestation is published on Ethereum, they submit the proof path for verification. The Ethereum contract recomputes the Merkle root from the provided path and compares it to the stored root to confirm the proof's authenticity. If a proof belongs to a valid Merkle tree attested by zkVerify, it confirms that zkVerify successfully verified the proof on its own network. Publishing an attestation on Ethereum does not require calling verify proof. The publish attestation function simply saves the last Merkle root on Ethereum. Verify proof is called by the user not during attestation publishing. It allows the user to confirm that their proof is included in the Merkle tree stored on Ethereum. Instead of verifying a proof directly on-chain, which is computationally expensive, zkVerify verifies it off-chain and posts only the Merkle root on-chain. So that means that verification on Ethereum is reduced to checking a Merkle proof only, a process involving only hashes, making it significantly cheaper. Users must submit their proof to zkVerify, listen for verification events, retrieve the Merkle path, wait for the attestation event on Ethereum, and only then call verify proof on Ethereum. An event is emitted on zkVerify when a proof is verified and a Merkle root is generated. A bridge relays this to Ethereum, where another event is emitted. Once the Merkle root is stored in Ethereum, the user calls verify proof, ensuring that their proof exists within the stored Merkle tree. Users' contracts must recompute the statement hash and call verify proof on zkVerify's Ethereum contract to ensure the integrity of the verification process. With our new flow, we allow users to specify the chain where their proofs should be published. Users must cover the cost of computing the Merkle root and bringing it to their chosen destination chains, ensuring that the attestation is correctly published. Users cover the cost of associated expenses, but these costs are distributed across multiple users submitting proofs. A larger proof list reduces per user cost, but increases the time required for an attestation to be published. If the list is too big, proofs take longer to appear on Ethereum or any other L1. Larger lists lower cost but delay attestations. Smaller lists increase fees but speed up verification on Ethereum. Guess you cannot have both. The balance depends on the blockchain's cost structure. In a Web2 scenario in zkVerify, users submit the proof to zkVerify and wait for verification. In a Web3 scenario, however, proofs must be relayed to a blockchain for decentralized verification. While Web2 apps may lack the ability to integrate proof verification themselves, relying on zkVerify for this functionality, this approach introduces latency concerns. zkVerify's Web3 verification flow has an average delay of about 5 minutes, which makes it a bit impractical for real-time applications such as real-time login with zero-knowledge proofs. To address verification latency, zkVerify introduces optimistically verify, which allows applications to proceed with assumptions based on the local pre-check. Like Ethereum's estimate gas, Substrate's dry run allows users to locally execute an extrinsic or transactions, if you like, before submitting it to the network. The optimistically verify function performs a local dry run of proof verification. If successful, users proceed with their application while the actual proof submission runs synchronously. So to recap, let's try and actually draw our architecture. So here, let's say we have some sort of user, and here we have our proof submission interface. Within our proof submission interface, we'll have a couple of methods, and user will interact based on the inputs. So user will give verification key, proof, and public inputs. Here we're going to have register VK that accepts verification key. We will have submit proof. It will accept verification key, proof, and public ends, meaning public inputs. Here we'll have list of verification keys, and that will make for verifier palette. So that can be any of the verifier palettes that we have. So what happens next? As we're going to emit proof verified event if the proof is verified. It goes like this. What will it contain? It will contain a hash of bunch of things, hash of hashes to be precise. It will have kachuk, hash of verifier ID, hash of vk, sorry about that, and hash public inputs. So this will work with proof of existence palette, which will have a couple of methods of their own, and it will contain a list that will be very important for a Merkle tree later, we will going to see. So it will have verified proof. It's going to be a list. So everything from here, it will become point here. And this is a fixed number that determines the length of the list. So later on we will have publish attestation, and we will have proof path with statement hash. So this is all within the proof of existence palette. So these two will give info to Merkle tree. So this would be Merkle root. This is how it builds. So it has two more, then two more. And this is where they go, so it will become one of those leaves. So from here, we will go to event attestation, which will accept Merkle root. From here, we will have Merkle path. User will submit his vk proof and public inputs because we will use bridge here. Sorry. That will bring us to one. This one, let's say Ethereum. So here we'll have vk proof public input from this side, and here we'll have Merkle path. And on one L1 Ethereum, we'll find two contracts. One will be zkVerify. The other one will be user, and they have different methods that you can call, and it can be called within the zkVerify or within user.sol. So one thing that we have here is attestation, publish attestation, and verify proof. That's all within this one. And the other one will have verify proof and also recompute attestation. And this is calling your user contract and solidity on L1, such as Ethereum, is making sure that you actually have good proof verification on zkVerify. And yeah, I think this is it in a nutshell, how zkVerify works. And guys, if you have any sort of questions, you can always ping us either on Twitter, on Discord, or our Telegram groups. Or if you see us at some sort of events, you can also ask us questions about this. And yeah, we'll be definitely eager to help you and see more builders come to zkVerify. Thank you so much for watching.